That's a lot of information very quickly. These are equations that you probably are familiar with from dealing with reverse phase chromatography. If you're not real familiar with them, I think that probably would help you in your achiral chromatography. Just do a little reading in fundamental text on liquid chromatography. Discussion is much more in depth than what I just went through. So there are some special considerations in chiral chromatography. The principles of chromatography apply to chiral chromatography, as I said earlier. Chromatography is a partitioning of the analyte between stationary phase and mobile phase. So these equations that I showed you a little bit ago apply whether it's chiral chromatography or achiral. What makes chiral chromatography somewhat mysterious or difficult is the separation mechanism is a little more complex than, say, reverse phase chromatography. We typically have weak polar stereoselective interactions between analyte and chiral stationary phase. The effect of the mobile phase is often more pronounced in chiral chromatography than, for example, in achiral chromatography. So this will give us an extra parameter to change, but it's also an extra parameter to investigate. We're dealing with often the analysis of the wrong enantiomer. We're usually interested in what the level of the impurity enantiomer, the undesired enantiomer is. Usually don't analyze racemates. In chiral HPLC, the separation is typically driven by selectivity, and the isomer ratio is usually a factor of 100 to 1 or 1,000 to 1 or 2,000 to 1. So I'll just talk a little bit about the chromatography. I want to talk about the particle size or column efficiency. And you probably know this from achiral chromatography, that with smaller particles, we get higher efficiency. Efficiency is related to 1 over the diameter of the particle. So as we go to smaller particles, we'll get higher column efficiency, which means we'll get higher resolution. But we also get higher pressure, and this certainly is the issue of UHPLC. UHPLC, as you probably know, is not really a technique. It just means chromatography run using smaller particles, which result in higher pressure. But with smaller particles and sharper peaks, we also get taller peaks. The area is conserved, so we'll get a taller peak, which improves our limit of detection and limit of quantitation. So this can be very valuable in performing an analysis of the low-level enantiomer. There's also some advantages to using a shorter column. We have shorter analysis time. Obviously, from the shorter column, we have lower pressure, so we may be able to run at higher flow rate even and reduce analysis time further. As we discussed earlier, the retention factors are unaffected by flow rate. And this is a little counterintuitive, but on shorter columns, you also get taller peaks. This is a summary of what I just said. This is a little clue as if you want to work this out for yourself, but because the peak width changes as a square root of the column efficiency, if we say double the column efficiency by making the column longer, the peak width only increases as a square root of 2. So we will have a higher or a sharper peak relative to the retention time on shorter columns. And that's often discussed in fundamental books on chromatography. If you want to discuss it, I'd be glad to talk to you about it. And I will say I've had discussions with people who are very good chromatographers who have had to think this thing through, that it seems intuitively that, oh, longer columns should give you a higher column efficiency, and therefore the peaks will be sharper. So as we go from smaller particles, we do increase the column efficiency. So we have about a 5/3 increase in the column efficiency, going from 5 micron particles to 3 micron, and we have the equivalent decrease in column efficiency going to the shorter column of about 3/5. Those cancel out. So for going from 5 micron to 3 micron and going from 250 millimeters to 150 millimeters, we should have about the same column efficiency, but we have about 60% of the analysis time. So we've reduced the analysis time. These peaks are not on the same, they're on the same time scale, but not the same response scale. But we can see that these peaks are sharper, so they will be taller because area is conserved. So this gives us an advantage. We see the same general behavior going from the smaller particles Um, I want to point this out. This illustrates two things. One is this isn't just a change from particle size. This, I think, is probably just a lot-to-lot variability. So, and we'll discuss this, and we do this in achiral chromatography too. We'll use multiple lots in part of our validation, different lots of stationary phase. But one of the other issues is you don't want to have just good enough separation in your method when you develop it. You want to have some leeway so that if there is some variability in instrument to instrument, or some variability in a stationary phase or whatever, that you have enough resolution to overcome some slight differences in the observed resolution with your method. So part of making a robust method is not to have just barely have separation. You want to have plenty of resolution. We go to a smaller particles yet, go from the 3 micron to sub 2. We get further increase in sharpness of the peak. Again, not on the same time response scale, but these peaks are taller because the area is conserved. And we got back some of our resolution, partly because we went to smaller particles, but also probably a lot-to-lot difference. And I'd certainly point out again, the lot-to-lot variability is an issue that you probably have encountered in achiral chromatography. Separation mechanism in chiral separations is different than we typically see in reversed phase or normal phase or helic or other separation techniques that you may be familiar with. In achiral chromatography, we're used to seeing things like C18, which is fairly lipophilic stationary phase and pretty first order interaction between analyte and stationary phase, just a partitioning principally on bulk polarity. We can add some functional groups and change maybe a little bit of selectivity and add some polarity, so increase the retention of polar compounds. But basically, we're looking for a single mode interaction. They're fairly predictable. Don't want to spend a lot of time on this slide, but it shows us a lot of things. We know something about allotropic strength of alcohol, like methanol versus acetonitrile. We know ACN is a stronger solvent, so typically 40-60 acetonitrile water is the same allotropic strength as methanol 50-50. I think in the tables that I was looking at, it was like 41 to 50. So that's the mobile phase I used. And we get almost identical separation. There's a little less retention in acetonitrile for these benzyl alcohols. But notice this order of elution is predictable. The more polar the compound, the less it's retained. So the toluene, which is just a methylbenzene, is the most retained. It's the most lipophilic. This ether, anisole, is more polar than toluene. So it's less retained, and the benzyl alcohol is even more polar, so it's more retained. Notice both of these compounds have stereogenic or chiral center, so either the parafluorophenethanol or phenethanol itself are the enantiomers are resolved. We have an achiral column, so we're not going to get any difference in behavior for the enantiomers on that column. To get separation of chiral compounds, we need to use a chiral stationary phase. So the interactions of the analyte with the stationary phase, instead of being bulk properties, are generally stereoselective or stereospecific interactions. They're generally weak polar interactions, so hydrogen bonding, dipole-dipole interactions, pi-pi bonding, etc. So in this example, if we have stationary phase, which has, just to make up examples, say a hydrogen bond acceptor, and this is a pi base, and this is a dipole. If we have a hydrogen bond donor and we have a pi acid and we have the dipole of the opposite orientation, these will interact strongly, and so there's a good chance we'll have good retention. If we have the fit isn't so good, if we may get retention between, say, the hydrogen bonding, but the pi base and the dipole may not fit as well as the pi acid pi base, and same thing here with the pi acid and the other dipole. And so we may get less retention, less fit, good fit, and so we get it's less retained. With this good fit can sometimes come at a price. We have more interactions. Think about in achiral reverse phase chromatography, we deal with the dreaded secondary interactions, such as the interaction of amines with silanols. We try to disrupt that secondary interaction. Here, we don't have secondary interactions, we have tertiary interactions at a minimum. Sometimes we have quaternary or higher levels of interaction. We have 4, 5, 6 chiral sites that may interact with the isomers. We need at least 3, but we sometimes have more. So there's always a possibility of having, say, a sluggish off rate with one of these interactions. And so often the more retained compound is broader and may sometimes tail in chiral separations, more so than you would predict in say, typical reverse phase chromatography. Separations are less predictable in chiral chromatography. That can make them interesting, but that can also make it challenging. This just shows, I won't get into stationary phases, but we have difference of retention. Chiral-Pac IA is one of our best columns. We find a lot of separations on IA. In this case, it didn't give very good separation. Chiral-Pac IB gave a little bit better, and Chiral-Pac IC gave even better. Well, look at the structure of the molecule, on the structure of the stationary phase. Very difficult to predict that. We have to do that as an experimental process. So we typically just do column screening and typically use a fairly strong mobile phase just so we make sure everything comes off fairly quickly. In this case, on our Chiral-Pac IF, we got pretty good separation. We got some retention of IE and a little bit of retention on ID. So we probably investigated those using weaker mobile phase. In fact, on the ID, using a weak, going from 50-50 hexane ethanol to 80-20, we in fact did find a separation. This actually came from one of our application notes. I didn't do this experiment, but in looking at it, I would have thought, okay, we got the retention factor is around 5 or so. So I would have thought we could probably reduce retention and still get a pretty good separation. And so thinking about kind of the backwards way of thinking about this diminishing return is, on the other hand, if there's a diminishing return and an increasing retention factor for improving resolution, maybe if we decrease retention, we pay a small price and less resolution. So I don't have the experimental details, but I would expect that we would probably get faster analysis with going to lower retention and probably still have adequate resolution. But it'd be certainly an experiment worth running. So maybe try 70-30 on this. This just shows retention factor of, on this column, about 2.7 milliliters for a 250 millimeter column. So 1 mil a minute, that'd be about 2.7 minutes. So there's 1, 2, 3, 4, 5 additional column volumes. So it's a retention factor of 5. We also see differences in retention on different stationary phases. OD and AD are somewhat similar stationary phases, but we got reversal of elution order. This is the UV chromatograms, and this is just, we have an inline polarimeter with this analysis. And this just shows that, sure enough, you can have a reversal elution order. So sometimes people will talk to me about the first isomer, or first enantiomer. It depends on, that's not a physical property. It depends on the which stationary phase you're using, or mobile phase, as we'll see. This can present a problem with racemate. You don't necessarily know what the order of elution is. So either you need to have the individual isomers, or you need to have an inline polarimeter, but then you still need to know optical rotation of the isomers. The other thing I want to point out, this is some work we did with the US EPA on some organophosphorus pesticides. Phosphate is is tetrahedral. See the little tetrahedron, and so just like carbon, so it's also can have a stereogenic or chiral center. So many of the organophosphorus pesticides are in fact chiral. The mobile phase is often more pronounced in chiral chromatography than example in achiral LC. And I showed you the example of achiral in reverse phase chromatography where changing acetonitrile or methanol to acetonitrile caused very little difference in the actual selectivity. In chiral separations, it can be dramatic because different alcohol can have slightly different interactions with facilitating the interaction of the analyte with the stationary phase, or the orientation of the stationary phase, or the orientation of the analyte with respect to each other. So in screening, I would have run methanol, ethanol at a 1-to-1 ratio. When I saw this, I thought, well, this is interesting. Let's see, probably in changing one of the alcohols will, increasing one of the alcohols would improve separation. I had an inline polarimeter, but I also had isolated or separated these enantiomers, so I had spiked the sample with one of the enantiomers so that I could track order of elution in screening. So as I went to 3-to-1 methanol to ethanol and 1-to-3 methanol and ethanol, I saw a difference in retention. I got or separation. I got an improvement in separation, putting more methanol in the mobile phase. Looked like they co-eluted with more ethanol or less methanol in the mobile phase. So I thought, well, we probably just ought to try 100% methanol. That's probably going to give a pretty good separation. I wasn't thrilled with the tailing peaks, but it was probably adequate for this analysis. But I also thought, well, let's just see what happens with ethanol. Are we going to get any additional separation, or do you suppose we might just have an order of elution reversal? And sure enough, the elution order reversed. So ethanol to methanol, we would not expect, we wouldn't use ethanol in reverse phase chromatography typically because of the viscosity, but we would expect a pretty similar chromatography. And sometimes in chiral separations, we see this no difference. Sometimes we see a big difference. This is not particularly important to this separation, but it illustrates an example. So if we have a single component ratio of the alcohols, we can plot their effect on the retention of the two enantiomers. And just looking at this plot, we can see that the minus isomer, as we increase the ethanol concentration, the retention time decreases. And I guess we could have seen that just by inspection, looking at that. But by plotting the data, that gives us an idea of how it works. I just use Excel just to connect the dots, so to speak. The plus isomer, interestingly, the minimum retention occurred at like a 1-to-1 ratio of methanol to ethanol, and we got more retention with 100% methanol and 100% ethanol. That's not particularly important in this separation, but this is the sort of thing that you may want to know in doing method development or method troubleshooting or method validation. And so I think plotting the data, if I just looked at 1 or 2 data points, particularly if I looked at this one and looked at this one, especially if I'd not had a way of isolating the two enantiomers, such as a chiral detector or a difference in a concentration, I would have thought, oh, it doesn't matter whether we go from methanol or ethanol. But by increasing a few data points, I think we can see in a systematic way how the behavior occurs. Again, this is probably not particularly profound for this example, but it'd be a little more noticeable in some additional following examples.